Swayam Prabha. Digital India. Educated India.
Hello and welcome. We are on lecture number 24. We'll continue with our discussion on B-spline basis functions. In the Leibniz formula, let's consider the last three terms of the kth divided difference of HKS colon T. So the last term will be HK Ti minus K Ti minus K plus 1 up till Ti colon T S minus T truncated. Here S will be equal to Ti. The last but one term will be HK Ti minus K Ti minus K plus 1 up till Ti minus 1 colon T times the first divided difference of S minus T truncated. That would be equal to alpha I minus 1 Ti minus 1 minus T truncated plus alpha I Ti minus T truncated. And of course, there would be a plus sign here. And the third from the right hand side term would correspond to HK Ti minus K Ti minus K plus 1 up till Ti minus 2 colon T times alpha I minus 2 Ti minus 2 minus T truncated plus alpha I minus 1 Ti minus 1 minus T truncated plus alpha I Ti minus T truncated. So once again, the last three terms of the kth divided difference of H sub K S colon T are this expression plus this expression here plus this expression. You would know what alpha I minus 2, alpha I minus 1, alpha I would be. They would relate to W prime. You would know that. And I'm not really bothered about what these constants are at this time. Let's concentrate on the last term here. Let me call this term TL. Let me call this term here TL minus 1 and this term here t L minus 2. L corresponds to the last term here. So let's concentrate on t sub L. All I'm interested in doing is to figure which of these terms will be 0 and which will be not 0 for values in between ti minus k and ti. If you look at this term is ti minus t truncated. For t greater than ti, this term becomes negative, because of which this term here would become 0, irrespective of whatever this is. So TL for t greater than ti is 0. How about for t smaller than or equal to ti? Now this term here becomes positive, and this term here will not be 0. I would not know about this term as yet. I would assume that this term is non-zero as well. So I can say that TL is not equal to 0. So there is a very high likelihood that this term gets retained. So this term is important to us. Now let's concentrate on TL minus 1. And let's concentrate on alpha I minus 1, ti minus 1 minus t truncated plus alpha I, ti minus t truncated. Clearly, for t greater than ti, TL minus 1 is equal to 0. Why? Because this term is negative and this term as well is negative. Because of this truncation sign, this term and this term, they are both 0. Now for t smaller than or equal to ti and greater than ti minus 1, what happens? Look at this term here, ti minus t truncated. Since t is smaller than ti, this term here becomes positive. And so this term is not 0. How about this? Ti minus 1 minus t is still negative. And because of this truncation sign, this term is 0. Now let's concentrate on this term here. Can you figure what this term is? This is the k minus 1th divided difference of h sub k. The last number here corresponds to ti minus 1. The first number here corresponds to ti minus k. Now for values of t greater than ti minus 1, what would you say will happen to this function? Would it be 0? I would think so. And let's verify that. So h sub k, ti minus k, ti minus k plus 1 up till ti minus 1 colon t will be very similar to this expression here. It will be a linear combination of terms like ti minus k minus t truncated raised to k minus 1 plus alpha I minus k plus 1 ti minus k plus 1 minus t truncated raised to k minus 1, and so on and so forth. Now, when you place the last knot as ti minus 1, this is ti minus 1 right here. Change this index to I minus 1. And for values of t greater than ti minus 1, you would notice that all these terms, they will be negative, and because of which this entire expression will be 0. And so hk ti minus k ti minus k plus 1 up till ti minus 1 colon t, this expression here will be 0. So to summarize, this entire expression here, TL minus 1, for values of t greater than ti minus 1 would be 0. It is only for values smaller than ti minus 1 that this expression here will be non-zero. And let's worry about those. So for t smaller than ti minus 1, smaller than equal to ti minus 1, this is non-zero here. Now, what do you have to say about these two terms? I would want you to be very careful. This term here is positive. This term here is positive. So I can drop the truncated sign. The second thing, and a very important thing that you would want to notice, is that this term actually corresponds to the first divided difference of a linear polynomial. Once again, this term would correspond to the first divided difference of a linear polynomial, a linear pure polynomial. What would that mean? This would mean that this term will become 1. And we have seen this using examples in previous lectures. In general, the kth divided difference of degree k pure polynomial is 1. So TL minus 1 becomes important for values of t smaller than ti minus 1. And so I would say that this is not equal to 0. Now, let's go to the third last term here. And we are going to be using similar arguments. Look at this expression over here. And in particular, look at this last number, ti minus 2. What do you have to say for values of t greater than ti minus 2? If you come back over here, and instead of I, if you place I minus 2, we'll see that for values of t greater than ti minus 2, all these expressions, they'll become 0. What would that mean? This would mean that this term here is 0 for t greater than ti minus 2. Let me write this thing down for you. For t smaller than ti minus 2, this term will be non-zero. What would happen to this term here? Alpha I minus 2, ti minus 2 minus t truncated, plus alpha I minus 1, ti minus 1 minus t truncated, plus alpha I ti minus t truncated. This term here will be positive, this term here will be positive, and this term here will be positive. So in a way, we are looking at the second divided difference of a pure linear polynomial. Your alpha I minus 2, alpha I minus 1, and alpha I are set in that fashion that this expression represents the second divided difference of a degree 1 pure polynomial. And you know what that is. This is equal to 0 for t smaller than ti minus 2. And look at this combination here. For t larger than ti minus 2, this is 0. For t smaller than ti minus 2, this is 0. And if you extend this argument to all the terms before this term, you would see that all those terms will be 0. So we will be left with only TL minus 1 and TL. So in summary, the kth divided difference of this function here, which is hk ti minus k ti minus k plus 1 up till ti colon t, will be equal to this term here, which is h k minus 1 ti minus k ti minus k plus 1 ti minus 1 colon t times, you would know that this is 1 plus this term here. This is equal to h k minus 1 ti minus k ti minus k plus 1 ti colon t times ti minus t. Since I'm considering values of t smaller than ti, I can drop this truncated sign. So I'm not going to be using the truncated sign here. I just realized that I have made a little mistake here. This thing should be hk minus 1. Likewise, this is hk minus 1, and so is this. You might want to make corrections in your notes. Obviously, this is so because here I have hk minus 1, and I have been computing the divided differences of hk minus 1 all along. Now coming back here, what would you say this is? This is the kth divided difference of truncated power function of order k or degree k minus 1. So by definition, this should be a spline. this should be m k, the last knot is I of t. Also, this is psi k I t. We have considered both conventions or both notations. You are free to use either psi or m. K is the order, I is the index of the last knot. What do you have to say about this? Look at these knots here. So this would correspond to the k minus 1th divided difference of hk minus 1. What is hk minus 1? hk minus 1 is s minus t truncated k minus 2. This is the truncated power function of order k minus 1. By the same argument that we have used here, this corresponds to the k minus 1th divided difference of order k minus 1 truncated power function. So this would be a spline, a B-spline basis function. What is the order? The order is k minus 1, of course. And what would be the last knot? The last knot would be I minus 1. In terms of psi, this is psi k minus 1 I minus 1 t. How about this? Now we will have to be quite careful here. These knots convey that this expression here is the kth divided difference of order k minus 1 truncated power function. It may be a little difficult for us to think about this as a spline as of now. We will have to convert this expression suitably. How do we do that? So I can write h k minus 1 t I minus k t I colon t as, I'll have to be a little careful here, h k minus 1 t I minus k plus 1 t I minus h k minus 1 t I minus k t I minus 1 colon t. I'll have a colon t here, over t I minus t I minus k. What have I done? I have written the kth divided difference in terms of two k minus 1th divided differences. So this is a k minus 1th divided difference of hk minus 1. hk minus 1 is the order of this truncated power function. Likewise, this is also the k minus 1th divided difference of s minus t truncated k minus 2. Now, by definition, these two are splines as well. What would this be? First the order, then the knot. So this is m k minus 1 I of t. How about this expression here? Again, first the order, then the last knot. This is m k minus 1 I minus 1 t. I am now ready to combine the entire information into a recursion relation for B-spline basis functions. So I start with mkit equals m k minus 1 I minus 1 t plus ti minus t over ti minus ti minus k times mk minus 1 I t minus mk minus 1 I minus 1 t. What do we observe here? We observe that a B-spline basis function of order k can be written in terms of two B-spline basis functions, each of order k minus 1. The first B-spline basis function is m k minus 1 I minus 1, and the second B-spline basis function is m k minus 1 I. This is your recursion relation. I'll try to give you a general proof of the Leibniz result for the divided differences. So you would know what Leibniz result for divided differences is. Given a function f of x, and if that function can be written as a product of two functions g of x and h of x, the nth divided difference f square brackets open x0 x1 up till xn square brackets closed. So the nth divided difference of f is given by summation index r going from 0 to n, the rth divided difference of g, that is g within square parenthesis x0 x1 up till xr, times h within square parenthesis xr plus 1 up till xn. In the previous lecture, I had shown this result to be true for a few cases, namely for the first divided difference f x0 x1 and for the second divided difference x0 x1 and x2 in f. Today I'll try to give you a general proof of this statement. This proof is from Carl de Boer. The book is called The Practical Guide to Splines. Okay, so let's get started with the proof. We have a function f of x written as a product of two functions g of x and h of x, and then we have a set capital X of x values x0, x1 up till xn. We assume that we know fxi, which is equal to gxi times hxi for all I going from 0 to n. Let's start using some tricks. What this statement would mean is that there would be n plus 1 values of g of xi available to us. Using that, let's try to construct a degree n polynomial to represent gx. Recall the Newton's interpolation formula. A polynomial of degree n in x is given by alpha 0 plus alpha 1 x minus x0 plus alpha 2 x minus x0 x minus x1 plus alpha n x minus x0 x minus x n minus 1. This is of degree n in x. And of course, you would know that alpha 0, alpha 1, alpha 2 up till alpha n are all divided differences. Now let's express this result to represent gx as a polynomial of degree n. So g n x equals, I'm going to be writing the divided differences directly as per the notations that we know. So g sub n of x equals g square x0 plus g square x0 x1 times x minus x0 plus g square brackets x0 x1 x2 times x minus x0 x minus x1 plus some more terms, and then the last term will be g x0 x1 xn square parenthesis closed x minus x0 x minus x1, and then the last term here will be x minus x sub n minus 1. In short, I would be able to write the expression for g and x as summation index k going from 0 to n, g within square brackets x0 x1 x sub k square brackets closed x minus x0 x minus x1 x minus x2, and the last term will be x minus x sub k minus 1. We'll need this result, so we'll try to block it as of now. Now we'll do something very similar for h of x as well. We have n plus 1 values of h of xi available to us. It should be possible for us, therefore, to construct a polynomial of degree n in h as well. But we'll use a slightly different trick. Instead of going from x sub 0 to x sub n, we'll reverse the order. So h sub n of x, this is the nth degree polynomial representing the function h of x. This is equal to h xn. We would want to be careful because we are working with the reversed order now. H of xn is the 0th divide difference, that is the value of h at x sub n, plus the first divide difference involving xn minus 1 and xn, times x minus xn. Remember again that we are working in the reverse order, plus the third term will be h xn minus 2 xn minus 1 xn times x minus xn x minus xn minus 1. Plus, let's write the fourth term as well, h xn minus 3 xn minus 2 xn minus 1 xn times x minus xn x minus xn minus 1 x minus xn minus 2, plus there will be some more terms, plus try to figure out what the last term here would be. Again, we'll have the nth divided difference, and that would involve all values from x0 to xn. This is x0, x1 up till xn times, again we are working in the reverse order, x minus xn x minus xn minus 1, and the last term here would be x minus x1. Once again, we computed these divided differences in case of g from left to right in xi, and to compute the nth degree polynomial to represent h of x, we went the other way around. In short, I can write hn x equals summation index s going from 0 to n, h square bracket open x s plus 1 x s plus 2 up till xn times x minus xs plus 1 x minus xs plus 2 up till x minus xn. This is an important result for us, so we'll block it. Note the difference in these two expressions. The divide difference here involves x0, x1 up till xk. The divide difference here involves xs plus 1, xs plus 2 up till xn. The minimum value of s is 0. So, the starting value is x1 here. The starting value here is x0. With regard to these terms, we have here x minus x0, x minus x1 up till the last term as x minus xk minus 1. The maximum value of k is n. So, the last term here will be x minus x n minus 1 for k equals n. However, here the last term is slightly different. Here we have x minus xn. The starting term, of course, is x minus x1 for s equals 0. So, there are minor differences in the two expressions. Let's not lose our perspective. Recall that fx was equal to gx times hx. Let's now multiply the polynomial approximation of g with the polynomial approximation of h. So, gn of x times hn of x will be equal to summation, copy this expression here, k equals 0 to n g x0, x1 up till xk copy this expression here. So, I am rearranging terms h x s plus 1 x s plus 2 up till x n times the expression involving the x terms x minus x0, x minus x1 up till x minus xk minus 1 from here, and again the expression involving the x terms from here times x minus xs plus 1, x minus xs plus 2, x minus xn. Let me double check if I got this right. x0 to hk, xk, xs plus 1 to xn, that's okay. X minus x0, x minus x1 up till x minus xk minus 1, we are okay. X minus xs plus 1, x minus xs plus 2 up till x minus xn, we are okay. And of course, here we will have a double summation. Index s would also go from 0 to n. Let's worry about these coefficients a little later. What is of concern to us is this expression. Let me copy this expression down. X minus x0, x minus x1, x minus xk minus 1. Here we'll have some more terms, and then we'll have x minus xs plus 1, x minus xs plus 2, a few terms, last term x minus xn. There is a minor typo here. this should be x sub s here. Okay, now coming back to this expression. What do you think the degree of this part is? This is linear quadratic for x1. So if I multiply all these terms, I'll get degree k. In x. How about these terms? If I set s equals 0, then I'll have x minus x1, x minus x2 up till x minus xn, and that will have a degree n in x. So this expression will have degree n minus s. So the overall degree for this entire expression is n minus s plus k. Now let's come back. This here is a single term in this double summation. Now let's try to express this double summation as two parts. S going from 0 to n, k going from 0 to n. Let's try to express this as the summation of all terms for the case when k is smaller than or equal to s, and then summation of all terms for cases when k is greater than s. And let's try to investigate what happens to this particular expression for these two cases. Let's take this case first. K greater than s. So here k can assume values s plus 1, s plus 2, and so on and so forth up till n. Remember, the maximum value of k is n. Now concentrate on this part here. For k equals s plus 1, we have x minus xs. For k equals s plus 2, we have x minus xs, and then we have x minus xs plus 1. So if you notice, for all values of k greater than s, we will have terms involving x minus x0, x minus x1, x minus x2 up till x minus xn. What is the consequence? The consequence is that this entire expression will vanish for all xi, I going from 0 to n. Once again, for values of k greater than s, this expression here will involve terms like x minus x0, x minus x1, x minus x2, all the way up till x minus xn. there will be some square terms and so on and so forth. And this entire expression will become 0 for all values of xi for I going from 0 to n. So if you think about it, this part of the summation does not bother us. It is this part that we need to worry about. Okay, the first thing we need to do now is worry about the degree of the terms emanating from this summation for values of k smaller than or equal to s. Let's come back. You would know that the degree of the entire expression, which is here, is n minus s plus k. The maximum value of k can be s for this case, which would mean that the maximum degree of this expression here or of this expression here is n if you set k equals s. All right, so let's get our perspective back. Let me avoid all the confusion and let me rephrase or summarize whatever we have done so far. So f of x was being represented as the product of g and x, h and x, now will be written as summation k and s both going from 0 to n, but k has to be smaller than or equal to s. And then we have terms involving the divided differences. G x0 to xk, h xs to xn times the terms involving x's, x minus x0, x minus x1 up to x minus xk minus 1 times x minus x s plus 1 x minus x s plus 2 up till x minus xn. Now, since this part in the summation does not contribute to this result, what it implies is that it has to be this part, or rather this expression here on the right hand side, that would contribute to fxi equals gn xi times hn xi. And we have also seen that the maximum degree in x here will be for k equals s, and that would be n. In other words, this statement has to satisfy this equation for values of I going from 0 to n. Think about it this way. Like we approximated g and h using the corresponding nth degree polynomials, we can do the same for f. Okay, so using Newton's polynomial, we can write the nth degree approximation for f, and that would be f of x equals fx0 plus fx0 x1 x minus x0 plus fx0 x1 x2 x minus x0 x minus x1 plus, and the last term of course is the nth divided difference in f, and then x minus x0 x minus x1 up to x minus xn minus 1. Now let's try to compare the coefficients. Try to figure what would be the coefficient of x raised to n. Clearly, the nth divided difference in f. Coefficient of x raised to n is called the leading coefficient. Now let's try to come back here. This again pretty much looks like Newton polynomial in f in some manner. Let's try to extract all the coefficients corresponding to x raised to n from here. Remember that we'll get the degree n for this expression only for values of k equals s. And also remember that this is a double summation. So we set k equals s, then this coefficient becomes g x0 x1 x s h xs xs plus 1 up to xn. Now this expression corresponds to only one term here. How about incorporating summation in s? This is a double summation sign. The constraint here is only on values of k. So we incorporate summation in s, s would go from 0 to n. And so this expression would correspond to the coefficient of x raised to n. And for the Newton's polynomials to be identical from this result and from this result, these coefficients have to be identical. And if you notice, this is the Leibniz result for divided differences.